Welcome back. We are in week 7 of the program, a few more weeks to go. Very exciting. So today we're going to switch it up. We're going to come back and go deeper into linear differential equations. And for this, we have with us Dr. Dong An. He's going to talk to us about his exciting new work on linear combination of Hamiltonian simulations technique, which can bypass the need for spectral mapping and complex quantum linear system solvers. Dong is an assistant professor at Beijing International Center for Mathematical Research, and he has worked as a Hartree postdoctoral fellow at Joint Center for Quantum Information and Computer Science at the University of Maryland, and he received his PhD in applied mathematics from University of California in Berkeley in 2021. And we're very excited to welcome him to this program. Yeah, over to you, Dong.
Yeah, thanks. Yeah, thanks a lot for the very nice introduction and organizing this wonderful event. Thanks all for being here. And today's topic is about quantum algorithms for linear differential equations. And basically, like this talk is based on several works that we have been done during the past 3 years on like solving general differential equations and also like some specific equations, but like all the equations are linear equations. So yeah, so basically like for today's talk, there will be 2 parts. So I will just like first discuss so-called the generic quantum ODE algorithm. So basically like today's talk will only focus on linear ODE. That is like for, if you're interested in partial differential equations, then I apologize for that. But like I believe all of the algorithms can be applied to the partial differential equations as well after you perform some spatial discretization and then like use the ODE algorithms. But for the first half, it would about generic quantum ODE algorithms. That is like we would like to discuss several quantum algorithms that can solve a general ODE problem. And then like I think I will focus on the linear combination of Hamiltonian simulation, like as introduced earlier, but like I will also give a very brief overview of all of the linear ODE algorithms that the researchers have already developed. So after that, I will discuss something like called the tailored quantum ODE algorithms. That is like we will focus on some specific classes of the differential equation and hope we can get even better complexity. So that is my plan for today's talk. Okay, let's start with the first part. And for the generic differential equation algorithm, we first start with the problem setup. That is like what the problem, what the differential equation that we are going to study, and what is the goal of our algorithm. So basically, we will focus on this linear differential equation given in the equation at the top of my slide. This du dt equals negative AU plus B. So basically, like here we have it is a linear equation. It is an initial value problem. And we have a coefficient matrix negative A, and we have B of t, which is something like an inhomogeneous term. And then for the matrix A, so we assume it is quite general because like maybe like you are familiar with the Hamiltonian simulation problem or the Schrodinger equation. So in the Schrodinger equation, we have A to be an anti-Hermitian matrix. That is something like I times H, where H is your favorite Hamiltonian. And then that is the Schrodinger equation, which is like a very promising application for quantum computer to demonstrate potential quantum speedup. But like in today's talk, we will go beyond that. That is like we will focus on the general case. So I don't really put much assumption on A, but instead I'm assuming A to have a decomposition, which is given in the equation here. So this A equals L plus IH. And yeah, so here this L and H are 2 Hermitian matrices. And then basically, I would say this is a not real assumption. It's just like a different way of representing the matrix, because like for any matrix A, you can always define my Hermitian part L to be something like A plus A Dagger divided by 2 and H to be A minus A Dagger divided by 2I. And then you can verify that if I define L and H by these 2 equations, then I can always write A to be the combination of L and IH. So, and also you can verify that L and H are 2 Hermitian matrices. So basically they are 2 Hamiltonians. So this decomposition is not assumption, but just like a different representation. But I will make a real assumption on the matrix or on the Hermitian part L of this matrix. That is, I will assume my matrix L to be positive semi-definite. So this is a very restrictive assumption because like after this, with this assumption, our linear ODE dynamics will never grow. So the norm of my solution U will always remain at the same level, or it will have some kind of decay, but it can never grow. So this is like a very strong, what we call a stability condition. And unfortunately, we have to assume this kind of rotation for many of our quantum algorithms to work, because we can really prove that if my solution has a exponential growth, then basically no generic quantum algorithm can be efficient. So there's like some lower bound results on that. So yeah, these are the setup of today's talk. That is like I will discuss quantum algorithms for this differential equation, and basically for the matrix A, I will assume this kind of stability condition. And of course, for general linear ODEs, there are many applications. Like the Schrodinger equation is the very specific case that we discussed. We have already discussed, but we also have many other applications, like in measuring time evolution when the matrix is Hermitian itself. And this can also model the open quantum system dynamics, or non-Hermitian quantum physics, or like for many classical differential equations. This is also the general model. So, and I heard from the introduction that you have already learned something about nonlinear differential equation, and you know that for nonlinear differential equation, we can perform some linearization, and then after that, all the equations are reduced to linear ODEs. So we can also apply all the algorithms here. And so I discussed the linear ODE, but I haven't really answered the question what we mean by solving this ODE quantumly. So in today's talk, we will like by solving this ODE quantumly, we mean two things. So the first is like we probably want to have a so-called the history state preparation. That is like we would like to prepare a quantum state which encodes the trajectory of my dynamics in this quantum state. That is like I will have a time step size h, and then I want to like include the entire trajectory in a single quantum state. So this is what we call the history state preparation. Or sometimes we will like just only care about the final state. That is like the solution at my final time. So in that case, we will only need to compute this u evaluated at the final time t, and quantumly we will prepare a quantum state that encodes the information of this ut in its amplitude. So this is my setup. And for solving linear ODEs, actually, there have been many existing quantum algorithms. And in the next few slides, I will spend a few more minutes to give you a very brief overview of this field on this direction. So for generic quantum ODE algorithms, I would like to categorize them into two different types. So the first type is what we call linear system-based algorithms. So for this type of algorithm, the ideas are similar. That is like they will, for all of these algorithms in the first type, they will first perform some time discretization of my differential equation. That is like they will just do some discretize the time variable, and since my equation is linear, then it will transfer this continuous dynamics into a discrete evolution, which in turns to be a large linear system of equations. So and then what we will do is that we will apply our favorite quantum linear system algorithm. So for example, like you might already heard about HHL, but like we also have some more advanced quantum algorithms on that. And then like for example, based on LCU, based on QSVT, so on and so forth. But anyway, so this is the entire idea. That is, we first discretize the time variable. And then my ODE is reduced to a linear system of equations. And then we use our quantum algorithms to solve the linear system of equations. And then we're done. So this is the first type of the algorithm. And for this type of the algorithm, the first one was proposed by Dominic Berry back to 15 years ago. So in that algorithm, the time discretization is based on the multi-step method. And after that, there are like many follow-up works based on almost the same idea, but use different time discretization approach. So for example, like we have already developed many algorithms based on, let's say, truncated Taylor series, or even like improved version of the truncated Taylor series. And also for the time-dependent case, that is when my coefficient matrix A is time-dependent, then we can also like design this type of the algorithm based on the spectral method or truncated Dyson series, so on and so forth. So yeah, I would like to introduce in more technical details on how this type of the algorithm works. So here's like a very simple illustration of the linear system-based algorithms that I described in the previous slide in the more technical details. So here, what I'm taking is so-called the forward Euler method. That is like, okay, we start with this differential equation, du dt equals negative au plus b. And then what we are going to do is that we will first perform time discretization by forward Euler. So forward Euler really means that we just like approximate my derivative du dt by a finite difference. So by a finite difference of two steps, this kind of ut plus h minus ut divided by h, where h is my time step size. It's a very small, it's a small time step, it's a small real number. So after this kind of discretization, we can see that, okay, this equation, this discretized ODE is a linear evolution between ut and ut plus h. That is like it mapped this ut linearly to this kind of ut plus h. And then the next step is that we would try to formulate my history state, the entire trajectory of my ODE as a linear system. So what we would consider is the large linear system right here. That is like, so we construct a linear system and the solution would be my history state, UH, U0, UH, U2H, all the way to UT. And then we can verify that. So now we can really put this kind of a discrete evolution into our coefficient matrix to form a block matrix. That is like for the first line, we would put an identity, and then you can check that this corresponds to my initial condition. So this is the trivial line. It doesn't really matter. But starting from the second line, it is I have a negative I minus HA in this block, and I have another identity on the diagonal. So this you can verify that. So if we check the second line of my linear equation, then this is actually the discretized ODE at time t equals 0. So this is the second equation. And then I will do the similar thing. That is like I will try to form my linear equation from UH to U2H, U2H to U3H, all the way there. So basically I will have a very large block matrix, and on the diagonal I will have all of these identity matrices, and on the off diagonal I will have negative I minus HA. And then on the right hand side, of course, you can check. So for the first block, it is the initial condition, but for the remaining part, it is related to my inhomogeneous term. So yeah, so this is the equivalent formalism of my forward Euler discretization. And then now you can see that, okay, we have a large linear system of equations. And then to solve my ODE or to solve the history state preparation problem, what we can do is that we can just apply my quantum linear system algorithms like the HHL algorithm. And then, yeah, this is this is like the idea of the linear system based algorithm. And so this is the simplest one. That is like I only use the forward Euler, and for the linear system algorithm, I just apply HHL. But you can imagine that there are like lots of variants as I showed you in the previous slide. So basically we can change the discretization method, and then this will change the coefficient matrix we have in our linear system. And also we can apply like more advanced quantum linear system algorithms. And actually, so far, the best quantum linear system algorithm is proposed based on the kernel reflection as well as the discrete adiabatic evolution. All of the algorithm can achieve optimal scaling. So so and then we can really apply those kind of algorithm to have better complexity. So this is like the idea. So this algorithm is very nice for history state preparation, but you might ask, so what if we care about the final state preparation? So I would like to first mention that. So we can also modify the linear system-based algorithm for final state preparation as well by like adding some kind of so-called padding line to make multiple copies of my final solution. And then after that, after I prepare the history state, I can perform the measurement onto onto one of my auxiliary register, and then I can just extract the information from the history state for my final state. So this is possible, but this kind of technique usually require multiple copies of the right-hand side of my equation. So I will not like go into technical details, but this is the entire motivation on the second category of my differential equation, of our differential equation algorithm, which is so-called the evolution-based algorithms. So the evolution-based algorithms is, the idea is also very straightforward, or the motivation is straightforward, is try to directly implement the time evolution operator. Because like we know, so since here we only care about the linear equation. So if we consider the homogeneous case, that is like my equation, my homogeneous, the inhomogeneous term B is equal to 0, then basically my solution has a closed form representation, which is e to the negative at acting on my initial condition. So in this case, if we can just directly implement this operator e to the negative at, and then yeah, we're done, right? Because like if we can implement that, we only need to apply this onto my initial condition, and then we solve the homogeneous equation. But of course, for the inhomogeneous equation, as I showed you at the very beginning, so it can also be done if we know how to implement e to the negative at. So this is something what we call the variation of constants formula. So actually, this formula is given at the bottom of this slide. That is like, so the solution of ut can be represented in this very general form. So the technical details of this general form is not very important, but like the important thing is that, so it only involves two operators. So one is this e to the negative at, and another is this e to the negative at minus s, which is almost equivalent to the e to the negative at. So basically, like the short message is that if we can solve the homogeneous case, then we will definitely know how to solve the inhomogeneous case. But like to implement this e to the negative at is not very straightforward, because we know A is a general matrix. So in general, it is not a unitary matrix. Then we have to like use some different treatment from the Hamiltonian simulation algorithm. So along this line, you can see that so for this type of the algorithm, so the research only started just very recently, maybe back to like 3-4 years ago. So now we have like some of this type of algorithm, it evolves very fastly. So there's like a framework called quantum eigenvalue processing, which can solve this differential equation by eigenvalue transformation. But the quantum eigenvalue processing framework is even much more general framework. So it can deal with many other problem than this kind of differential equation. And also, like for this type of the algorithm, actually the first one is so-called the time marching approach, which mimics the classical evolution. And recently, there are like some idea by reducing the general time evolution operator into some Schrodinger equation or some Hamiltonian simulation problem. So here are like two of this kind of algorithms. So one is so-called the Schrodingerization. It's exactly reduce the general ODE, linear ODE into some Schrodinger equations. And in today's talk, I will mainly focus on the approach that we proposed based on so-called the linear combination of Hamiltonian simulation. So it is very similar to the Schrodingerization type of algorithm. So actually we share many of the similarities. So for the linear combination of Hamiltonian simulation algorithm, so I would like to show you this very main theorem that is like, so it is actually based on a very short observation that for any non-unitary evolution operator, which is the e to the negative at that I showed you in the previous slide, they can be written as a linear combination of Hamiltonian simulation problems. So technically, this result is stated in this theorem, but like the most important part is in the equation in the middle of this slide. That is like, so let's take a closer look at this equation. So on the left-hand side, we have our goal, that is our time evolution operator, e to the negative at. And on the right-hand side, so I have an integral. And inside the integral, so first I have this operator uk of t. So this is a parameterized operator, and this uk of t is defined through the equation at the bottom of this slide. So if we look at the definition of this ut, then we can realize that, so for this equation, so on the right hand, it is actually a Schrodinger equation. So it is a Hamiltonian simulation problem, because like here we assume that this L and H part, they are both Hermitian matrices, as I discussed earlier. So now I have a K parameter to be a real parameter. So this KL plus H is still a Hermitian matrix. And then I have a negative I in front of everything. So basically like the entire equation is nothing but a Hamiltonian simulation problem. And then, which means that my operator UK is a unitary operator. So which is very nice, because like we know many efficient algorithms to simulate that. But instead of only having one this UK operator, we also have like some other thing that is like we have a kernel function fk divided by 1 minus ik. And then basically like this f function is so-called a scalar valued kernel function that, and I will discuss this in details in next slide. But like the short message is that this is some scalar valued thing. And then if you look at the entire right-hand side, it's basically something like a continuous weighted sum of my unitary operator UK. So that is why we call this formula a linear combination of Hamiltonian simulation, although this linear combination is a continuous version. So the continuous linear combination is nothing but this kind of integral. Okay, so this is the equation that we found. I will not show the proof of this equation, which might be very technical, but instead, in the next slide, I will show you some special cases of this equation, which might help us to understand this equation more intuitively. So the first special case, so at the top is the repeat, it's another repeat of the equation that I showed you in my previous slide. So basically like here, this e to the negative I kl plus h times t is the UK operator that I showed you in the previous slide. So this is just like an explicit representation. But like the first special case is that if my matrix is anti-Hermitian, that is like in my matrix A, I only have H part. So I'm assuming L to be 0. Then in this case, my left-hand side becomes something like e to the negative iht. And then for this case, we can say that, okay, this is already a unitary operator, right? It's like, it's nothing but a Hamiltonian simulation problem. So on the right-hand side, since my L is equal to 0, then I will only have this e to the negative iht, which is another unitary operator, which is exactly the same unitary operator, and it is k independent, right? It has nothing to do with k. So the integral on the right-hand side is a trivial integral, right? It's just like an integral over my kernel function, fk divided by 1 minus ik. And then yeah, we know that, okay, so for this formula, it will definitely be true as long as our kernel function satisfies certain normalization condition, right? We only need to choose my function f such that my f over 1 minus ik to be normalized, that the integral over the real axis is 1, then yeah, then we're done. So this is for the first special case, which might be a bit trivial. But like, I would like to discuss a little bit non-trivial case, which is if we only have the Hermitian part. So here is on the right, that is like, I'm assuming that my matrix is Hermitian. That is, I'm assuming I only have L and H to be 0. And then now on the left-hand side, I have e to the negative LT, which is not unitary in general, because like now here, this operator actually corresponds to the so-called the imaginary time evolution, if you're familiar with that, but it doesn't really matter that much. So now the point is that here on the left-hand side, it's not a unitary, but on the right-hand side, so I have this e to the negative iklt inside my integral, which is again a unitary operator, but it depends on the variable k. So now on the right-hand side, it is the real integral. It's not that trivial. But for this formula, it is also quite, it might also quite familiar to some of you, because like this is nothing but what we call the Fourier transform, right? It's just like, it is basically saying that if we have the Fourier transform of my function f over 1 minus ik to be e to the negative x, then basically like the above equation would hold, because like this is just a matrix version of my Fourier transform. So this is again another specific example, and our real contribution is to combine these two equations together. So of course, like we cannot directly multiply these two special cases together, because like my matrix L and H, they do not commute with each other in general. So if we multiply them together, then basically we just have nothing. We just get nothing. But it turns out that, so actually we can just directly combine them together, and this is our non-trivial proof based on some contour integral formulas. So if you're interested, I would definitely like encourage you to check our papers in details. So yeah, this is some special cases, but like I would like to say a few more words on the Hermitian special cases. So actually, this kind of case shows some close relation between our formula and the Fourier transform, and this gave us a way of finding the satisfying kernel function f, just like by some Fourier transform. So here I'm going to discuss this kind of kernel function. So we have seen that, okay, we need the kernel function to be normalized. And we also need the Fourier transform of f over 1 minus ik to be e to the negative x. But here, another important thing that I didn't mention is that, so we don't really need the Fourier transform to be e to the negative x on the entire real axis. It's really because like, so here in the, maybe I just go back to the previous slide. So in the previous slide, I have my L matrix to be positive semi-definite for the stability condition that I introduced at the very beginning, which means that I only need to consider this LT to be positive semi-definite. So in that case, I only need my function, the Fourier transform of my function, to be e to the negative x on the positive real axis. So I don't really care about what what happens on the negative real axis. So this is the key point. And then which means that this would give us some kind of flexibility of choosing my kernel function, right? Because like actually to find this kernel function, one way we can do is that we can first construct its Fourier transform. So we only need to force the Fourier transform to be e to the negative x. And after that, on the left part, on the negative part, we can choose whatever we want. And then after that, then we just perform the inverse Fourier transform of my constructed function, and then it will give a kernel function, this f over 1 minus ik. So this is the way that we choose the kernel function. And actually, like in our works, we have found like multiple choice of the kernel function. So there's like a very simple choice, which is to choose f to be the inverse linear function. That is, we can choose f to be exactly 1 over 1 plus ik. And this pi factor is for the normalization. And then you can verify that, okay, they satisfy all the conditions that we have. And it corresponds to the Fourier transform, which is shown in as the dashed line on the figure on the right. So basically, like because you can check if we choose f to be the inverse linear function, then its Fourier transform after divided by this 1 minus ik would be e to the negative absolute value of k. So it's this kind of symmetric function. So this is a valid choice. And actually, this is the very first choice in our first paper along this line. But it turns out that this choice at this time, it is not the best choice because like it only has a first order convergence. So it's really because like, so if we look at this function, so it does not decay very fast. And the decay of this function is very important in our algorithm design. You will see this very soon. So actually, like in our follow-up work, we find we find much more choices of the kernel function, and for one of the choice, they can achieve so-called the near optimal asymptotic scaling. And actually, this is the equation that I showed here. So we can choose f to be something like inverse exponential function. So this function is a little bit technical. So but like, so the idea is that we just want to we just want to make our kernel function to decay faster, and then the fastest one is just like we put this kind of linear function inside the matrix inside the exponential, and then like we can make this to be near exponential decay. So but like it turns out that we cannot really make it to be exponential decay, so we have to shrink a little bit. That is why we introduce another parameter beta in between 0 and 1 to like shrink this kind of thing. So, but anyway, like we have this better kernel function, and actually this new kernel function that I'm showing you is the kernel function that we will use for all the linear combination of Hamiltonian simulation algorithm, and turns out that it can achieve a near optimal choice. So this is about the kernel function. And now I have introduced our LCHS formula, and I have introduced the kernel function, the choice of the kernel function. And the very good news is that we have explicit formulas. So in the design of the algorithm, you don't really have to choose your kernel function every time, but instead you can just directly use this kind of explicit formula. And we have verified that this is asymptotically, this is the near optimal one. And then, okay, we have the formula. And then next I will discuss how to design quantum algorithm based on this kind of formula. And the idea is also very straightforward. That is like we start with our LCHS identity, and then we use some kind of discretization. That's like, so first, since the integral is over the entire real axis, but we will just like truncate this kind of real axis into a finite interval from negative capital K to capital K. And here you start to see why we really need our kernel function to have a fast decay, because like if our kernel function has a faster decay, then we can choose a smaller truncation order, and this will reduce the computational cost that we have in our algorithm design. And then after this truncation, I will just further discretize this integral by a finite sum. So for example, like you can use whatever numerical quadrature formula that you like. So for example, like we can use the simplest Riemann sum approximation. That's we just use the average of many equidistant nodes over the interval from negative K to K. And then, yeah, this would be effective algorithm. And then after this kind of a numerical treatment, then we can really represent this LCHS or this time evolution operator as a real discrete linear combination of unitary operators. So here, then we can just like design our algorithm based on this discrete approximation. So for the algorithm design, there are two steps. So the first step is that we need to implement my unitary operators on my quantum computer. And then as I discussed earlier, this is the Hamiltonian simulation problem. So we can use whatever Hamiltonian simulation algorithm that we want. So for example, you might have already heard the Trotter formula, the product formula. So this is definitely like great. And we can use even more advanced algorithm like the algorithm based on quantum singular value transformation, or even some other, there are like many Hamiltonian simulation algorithm, or you can even solve this analog quantum computers. So this is also possible. So anyway, we only need to implement this Hamiltonian simulation algorithm by whatever you want. But after that, the non-trivial step is that we really need to implement a linear combination of those unitary operators, which in turn to be non-unitary transformation. So to implement this, actually there are two options. So for the linear combination step, we can use, let's say, maybe a quantum approach. That is like we also want to implement this quantum linear combination of unitaries technique, or this technique is also called the LCU technique. So as its name suggests, you can see that, okay, yeah, this is exactly a subroutine that is designed for implementing this linear combination. But like perhaps I don't really want to like go into like technical details of this LCU technique, but I just want to mention that this is a very powerful technique. So it can implement general linear combination of unitaries. And the idea is to construct a larger unitary, which is called block encoding, if you're familiar with that. So basically it's a larger unitary in a higher dimension. And for the larger unitary, I would like its subblock to be the linear combination of the unitaries that I have. So basically, I'm embedding this linear combination into a larger space. And for that larger space, I can construct a larger unitary evolution operator. So this is the idea of this linear combination of unitaries. So we can do this quantumly. But alternatively, we can also do the linear combination step classically. So this is like something that is very important, which is based on so-called the importance sampling algorithm. So this can give us some better quantum with shorter circuit depth. So I would like to discuss this maybe in a little bit more technical details. So, okay, so for this importance sampling-based algorithm, so we start with, again, the linear combination of Hamiltonian simulation for the solution, which is given on the top left. So since our solution can be represented as a linear combination of unitaries, then in this case, if we care about the observable of my solution, so for the importance sampling, unfortunately, we can only compute some observable. We cannot really like prepare a quantum state for that. But you know that in many quantum algorithms, so the observable is actually the final, the actual thing that we need. So if we want this observable, then actually this observable can also be written as a linear combination of many so-called the local observables. So by local, I mean that this observables only involves two unitaries, right? Because like for each solution, it is the linear combination of many unitaries. And then if we just combine this, just like do this kind of computation for the observable, then again, it is a linear combination of many so-called local observables involving only two Hamiltonians, two unitaries. Then our idea is that, okay, we will compute those observables independently on quantum computers. And then after that, I will just do this linear combination classically. So here comes the algorithm that is like, I will just like first like sample my index J and J prime with some probability, but this kind of sampling strategy is done on a classical computer. And then after I get all of these samples of my index, so we know all of these kind of coefficients, and then after we have those samples, and then I will just compute each observable corresponding to my samples independently on quantum computers. So for example, like here I'm showing you this kind of like illustration, but like the great thing is that so for each observable, it only involves two unitaries. So the overall circuit can be very short, and the size of the circuit can also be very small. Then after this, I will collect all of these observables, and then I will do the linear combination again classically. So basically, like you can show that. So for the final average, this would be an unbiased estimate of this kind of entire observable thing. And then like we have a really great algorithm for estimating the observable of my final solution. So this is the idea of the importance sampling. And So, and this is perhaps my final slide for my first half, which is like a comparison of the complexity of all of the algorithms of this LCHS algorithms compared to some other algorithms. So basically here we compare our LCHS algorithm with the best linear system-based algorithm on truncated Dyson series, and also the time marching algorithm, which is another evolution-based algorithm. And the message is that, so for all of the algorithm, for our LCHS algorithm, we can achieve so-called optimal state preparation cost and near optimal matrix query complexity at the same time. So for example, like if you look at the query complexity in terms of the matrix, then basically like our algorithm scales almost linearly in terms of the evolution time and polylog in terms of 1 over epsilon. So this is the optimal scaling. And also for the state preparation cost, we only have a parameter Q, which is the norm decaying rate. So this is something that we cannot overcome, but like we only have this parameter. So compared to, for example, the truncated Dyson series, we also reduce state preparation cost as well. So this is like the advantage that we have. So this is my first half of my talk, and I would like to take some questions for this part. And actually, I have already seen some questions in the chat. So
Do you want to read out the questions out loud? I put it in your chat.
okay, yeah, I can read the question. Yeah, I'm trying. Okay, so there's like the first question is like, what is the advantage by considering quantum algorithm if we have a better tool to solve it using power series method? Okay, so yeah, this is the great question. So I think the general methodology or the general idea of using the quantum algorithm is try to have some better algorithm for high dimensional ODE. That is like, so because like in many like classical algorithm, that is like we just have like the cost would scale at least linearly in terms of the system size. But for quantum algorithm, if we have under some strong condition, we can have only polylog dependence in terms of the dimension. So this is very similar to the advantage by the HHL algorithm. That is like once we have some great input model, then basically like we can achieve exponential speed up in terms of the dimension. So this is this is the motivation why we are considering the quantum algorithm. But like of course, like this claim is under some very strong assumption that is like we really need very efficient construction of my input model. So basically, we need to construct the input model, a very efficient model for my matrix and also for my initial condition. And also the readout problem is also like another issue. But I guess like the short answer would be like we, of course, yeah, we have actually like if the equation is linear, they would have many efficient algorithm classically, but our goal is try to be even more efficient in the dimension. So this is our hope and our motivation for considering the quantum algorithms. Okay, so there's like a second question. The performance of quantum algorithms like HHL is affected by properties like condition number. Is also this approach affected by such parameters? This is a great question, and the answer is yes. So the linear system-based algorithm, it's also the complexity is also affected by the condition number. And you will see this in the second half of my talk. That is like, so the condition number would typically scale linear in terms of the evolution time, and also like so that would increase the computational cost if my evolution time is very large. So for the evolution-based algorithm, actually maybe the answer is no, because like in the evolution-based algorithm, we don't really have a linear system, right? It's like we just have some kind of matrix operation, and then perhaps there's no analog. But for the linear system-based algorithm, yes, the complexity depends on the condition number. Okay, great. Is there any other question for the first half? Okay, I think there's like another one. Let's see, would the quantum implement of the linear combination part be more efficient if we use the linear combination of things instead? Yes, actually, like, yeah, this actually like the quantum implementation in general, it is more efficient because like if we count the overall quantum complexity, the quantum linear combination would be more efficient. So the reason why we are considering the classical linear combination as well is that actually the classical combination would increase the overall complexity, but it would make the circuit depth to be shorter. So there's like a trade-off but like it really depends on like which goal we would like to achieve. So if we really want the overall complexity to be optimized, then basically like we should really use the quantum notation. Okay, so here we are truncating the integral from negative k to k and approximating the integral into summation. So will it affect the solution as k its small value since truncated? Yeah, this is a great question, and this will introduce some extra error in the solution. So I'm perhaps I can go back to my truncation. So because we use this truncation, so we definitely like lose some information. So here what we have is just like it's an approximation thing. So we introduce some kind of error. But like in the algorithm design, this is not a big deal because we will carefully choose this kind of k to ensure that this truncation will not introduce that much error. So we will make sure that this truncation value k will depend on the error threshold. So for example, like if our target error is something like 10 to the negative 6, and then this k would be also related to that value. So for example, if we want our error to be even smaller, for example, if we want to like increase the accuracy from like 10 to negative 6 to 10 to negative 10, 10 to negative 10, then we would need to like increase the value of k accordingly. So yeah, I would say this will affect the solution. This will introduce some error, but like we have some nice control on that. Okay, great. Is there any other question for the first half?
No, that's what we got. We can
Okay,
keep going.
yeah, that's great.
Thank
Yeah,
you.
thanks for the great question. And then I will proceed to my second half, which is the tailored quantum ODE algorithm. So I have already shown you some generic algorithm, and you have already seen that. Maybe I should go back to the table here. So here in our generic algorithm, so we have this t-scaling to be almost linear. So if you also look at all the existing algorithms, so the best achievable scaling is linear in t. And actually, I would say this is something that we cannot beat if we only deal with the generic algorithm. So this is like something what we call the no-go theorem. That is like so if we want to like design a generic quantum algorithm, let's say for long time evolution, then basically like the best thing that we can achieve is linear in terms of the evolution time in my complexity. So this can be proved by something so-called the no-go theory for the Hamiltonian simulation algorithm. And also it is very physical because like we want to simulate the dynamics up to time t, then we have to pay this kind of cost. But we are always ambitious. We always want to do something that is even more efficient. So this is the goal of design this kind of so-called tailored quantum ODE algorithms, or what we call fast forwarding. So the goal of this fast forwarding algorithm is try to achieve a complexity which is even better than linear in the evolution time. And then just as I mentioned, so this is not possible for generic algorithms. So we have to reduce the number of the equation that we would like to solve. And then this is why we want to design some tailored algorithms for specific ODEs. And then here in the study of this type of fast forwarding algorithm is just like started maybe just like 2 or 3 years ago. So there's like very few work on that. But like in today's talk, I will only share with you like one specific case, which we call the dissipative ODEs. So for the dissipative ODEs, what we would like to do is that, so in the generic case, we assume our matrix L, the Hermitian part, to be positive semi-definite. But now I'm going to make it to be even stronger. I'm assuming this matrix to be positive definite. So that is, I have a real number, a real positive number eta, which lower bound the eigenvalues of my matrix L. So in this case, my matrix would be strictly away from 0, then it is a positive definite. And then what we can show is that in this case, my time evolution operator will always have an exponential decay. So it can never remain on the same value, but like it will always like have an exponential decay. And then this dissipative ODEs, of course, is an even special case of my ODEs showing at the beginning of my talk, but but fortunately, we also have many applications of this kind of dissipative ODE. So for example, like our favorite heat equation, it is a dissipative ODE after a spatial discretization. And also like for many like other equations with diffusion, then we can also like model them as the dissipative ODEs. And then for dissipative ODEs, if you want to design quantum algorithm, then the idea is that, so the idea is also quite straightforward. That is like since here in our time evolution operator, it has an exponential decay. Then my initial condition and my inhomogeneous term, they only affect the dynamics locally. That is like, so for example, like if we only look at the homogeneous part, right? If we just like don't have this kind of inhomogeneous term Bt, then basically like my solution will always decay exponentially, which means that my initial condition does not really have much influence on the long-time evolution. And also similar thing for the inhomogeneous term, that is like, for the, we can just take the, sorry, what? Is there any question?
No, I'm sorry. I think someone's unmuted.
Okay, yeah, no problem. Yeah, I can just go ahead. So you just like think our heat equation as an example, right? Like it's like, so if we want to, let's say, like simulate the temperature of the room that I'm currently in, then basically like I don't really have to go back to the very beginning when this kind of room was built, because like, so if you want to use the heat equation, the initial condition would be the time when this room was built, but like I don't really have to go back to that, because like the initial temperature of this room, all of the heat has already dissipated, so it doesn't really have any effect on the current temperature that I have here. So basically the thing that I only need to care about is maybe some kind of whether or not I turn on the air conditioner, or whether or not I have some kind of like heater during the past maybe 10-15 minutes. And then if I only take care of those information, then I can really predict the temperature of the current temperature of my room very accurately. So this is why we can really get better quantum algorithm, because like for the general dissipative ODEs, we don't really need to simulate the entire time trajectory, but instead we only need to focus on the very specific short time period. Okay, so this is the idea. And based on this idea, we designed two types of the algorithms. So we studied the performance of the linear system-based algorithms. And it turns out that for the linear system-based algorithm, so we don't really have any T dependence if my dynamics is dissipative. So here, the technical reason is exactly related to the question that we had in the first half, that is about the condition number. So basically, we have shown that if the differential equation is dissipative, is strictly dissipative, then the condition number of this large matrix does not depend on the evolution time. And in that case, if we apply our linear system algorithm, then the overall complexity does not depend on time. And the reason why the condition number does not depend on time is exactly the thing that I described earlier. That is like any perturbation in my initial condition, in my final solution, in my inhomogeneous term would only affect the dynamics locally. So we don't really expect any long-time behavior of this kind of thing. So there's no time dependence in the condition number. So this is our first result, and was proposed. It was analyzed in the paper showing here. So we also studied the performance of the LCHS algorithm, or even general evolution-based algorithm. And this is, in this type of the algorithms, we explicitly used our idea that is like we only need to simulate the short-time performance. So here the idea is based on this equation that is like we start with Duhamel's principle, the variation of constants formula. Then for the inhomogeneous term, for the homogeneous term e to the negative at, we can really ignore that because like it is exponential decay. So we don't really have this kind of dependence. And for the inhomogeneous term, we only need to track our dynamics back to a short time period T0. And then before this kind of time, it also does not have much influence. So this is like another truncation. And of course, it will introduce some truncation error. But fortunately, we can also control this truncation error, that is control this value, control the truncation error by tuning the value T0. So it will depend on the strength of the dissipation, but this is something that we can control. And then based on this, we also have a quantum algorithm. So here's like a comparison of all of these complexities that we have. So here in this large table, so for the first half of this table, you have already seen this in the first half. So this is the algorithm for the generic quantum ODEs. And then for the second half, they are fast-forwarded algorithms, which are designed for some specific case. And then here, the message is that, so if you look at our, for example, like fast-forward Dyson series method, which is a linear system-based algorithm, or our fast-forwarded chess algorithm, so for a history state preparation, we can always achieve at most logarithmic in terms of the evolution time. So for the LCHS algorithm, we even like fully remove the time dependencies. So this is exactly because like we don't really simulate the dynamics for the entire time period, but only for a short time period. And also for the final state preparation, so if you look at this LCHS algorithm or the evolution-based algorithm, it also does not depend on time. But like for the linear system based, it would depend on time. So due to some technical reason, adding some padding line. But like the great thing is that if you look at the best algorithm so far, actually like for dissipative ODEs, we can completely get rid of the time dependency. And this is also consistent with our intuition that for dissipative ODEs, we only need to care about the short time evolution for a very short time period. Okay, so I think I have completed all of my materials and I would like to have a short summary. So in today's talk, I introduced the generic quantum algorithms and also the tailored quantum ODE algorithms. So for the generic quantum ODE algorithms, so there are basically two types, the linear system-based algorithms and also the evolution-based algorithms. So I spend more time on our linear combination of Hamiltonian simulation algorithms, and it can achieve a near optimal complexity for solving linear differential equations. And also for the tailored quantum ODE algorithms, I discussed the dissipative ODEs, and actually we have many quantum algorithms which can fully eliminate the time dependence for this type of ODE. And there are like many interesting follow-up work that we can do. So for example, like we can try to like even further improve the complexity of our algorithm. And also, I think the more interesting thing is about the tailored quantum ODE algorithms. That is like, can we try to, develop like maybe like more types of the ODEs or even PDEs where we can achieve fast forwarding, or like for example, like, or we can just like design like general tailored ODE algorithms for like more practical examples. So I think those are like very interesting future works. And here are the references that I discussed in today's talk. So for the first two papers, they covered the linear combination of Hamiltonian simulation part. And for the last two papers, they are about fast forwarding. Actually, the last one is still an ongoing work, and we plan to post our paper in 1 or 2 weeks. So just keep an eye on that if you're interested. So with that, I would like to stop and thank you very much for your attention.
Thank you so much for that amazing talk. It was, very useful. Certainly learned a lot. Maybe I can like ask you a question.
Yeah.
Yeah, so one of the things you mentioned was like, how in the fast forwarding approach, how can it, like, I guess in general, a question is like, if someone wants to use this technique for one of their own specific application specific problems, what is a good place to start? What kind of properties of their problem do they have to understand or can they use to get better complexity?
Yeah, that's a great question. I think the starting point or the most important factor is to understand the rate of the dissipation in the specific example. That is like, so first you really need to check like whether, for example, like if I have a very specific equation. So the first thing is that I really need to check whether or not this equation is dissipative or not. So if it is not dissipative, then basically like we cannot apply our fast forwarded algorithm. But of course there might be some other fast forwarded algorithms, so then it will be a very interesting open question. But if the equation is dissipative, then what we need to do is that we need to understand the rate or the speed of this dissipation, or because like in all the design of the algorithm, we need to know that explicitly. That is like we need to determine the time period that we like to simulate, and it heavily depends on the dissipation. So after we understand everything, then I think all the algorithms that I discussed today, they're ready. So can just like directly apply all of these algorithms. So I would like to see the most important thing, or perhaps the only thing, is to understand the speed of the dissipation.
Thank you. Yeah, maybe just in one other general question, what does your like research approach looks like? How do you start looking at a research problem? It just can be an advice for some of our participants who are working on these research projects through this program. What kind of advice would you give to them?
Oh, that's a big question, and I'm not sure if at the right position to give advice, because like I'm still like very very, very junior. I don't really have much experience on that, but like maybe, yeah, if that can be helpful, then I can like share a little bit on that. That is actually like my background is from applied math. So I did my PhD in applied math. And actually like during my first 2.5 years, I knew nothing about quantum algorithms. I was working on something classically, like basically classical computational physics or like some density functional theory calculations. So that was my very beginning research area. But like I just switched to quantum algorithm because I found this is very exciting, and I think the that was not a very easy switch. But like I guess the thing that I learned from this kind of switch is that I would always start with something that I'm familiar with, because you see that I'm from applied math, so I'm familiar with, let's say, classical algorithms for linear system, for differential equations. Those are like some very traditional topics for classical numerical linear algebra and numerical analysis. And then now I just like, okay, I just switch to quantum algorithm. I just want to like design some quantum algorithm for those problems. So I would say if you just feel like to be very difficult to get started with, then perhaps a good thing to try is to start something that you are familiar with, and then like try to just like extend a little bit scope of this kind of thing. Maybe things would become better. Yeah. I'm not sure if that would be a good advice. So yeah, I'm still like learning like many things. So yeah, I hope I can give better advice maybe like 5 years, 10 years later. I don't know, but yeah, I hope that might be helpful.
No, thank you. That was a great advice already. Really appreciate it. Yeah, I see Josh is online. And yeah, thank you so much, Dong. This was an amazing talk. I certainly learned a lot, and I'm sure it was useful to a lot of the participants.
Okay, great. Yeah, thanks a lot.